Hello, welcome to this video. So in this video I will be doing a kind of derivation of the wavelength of matter, because in quantum physics matter in particles has wave-like properties, and I'm going to justify why the wavelength of physical matter is what it is. And this is an important derivation because understanding the wavelength tells you at what scales you can expect matter in particles to display wave-like behaviour, such as diffraction or interference. So this is an important derivation, and originally the way that kind of the de Broglie wavelength came about was through thinking of particles possibly having wave-like behaviour, because the photoelectric effect demonstrated that light, which we usually think of as a wave, has particle-like nature. So it introduced this duality, particles behaving as waves and waves behaving as particles. And the de Broglie wavelength says on what scales that duality should emerge for physical objects that we usually think of as particles. Now this derivation is going to be fairly informal, and I don't believe I've seen this before. It might not be new, but it's definitely not something I've come across. It's just something I've been playing around with in my head and thought was worth sharing, because I find it interesting that it can be derived from other equations. So let's derive the de Broglie wavelength. So the question we're asking is, what is the de Broglie wavelength? What wavelength does matter and particles have, or even humans? And to do this, we start with the equation for the energy of a particle of light, so E equals hf, where E is energy, h is Planck's constant, which essentially tells us at what scales quantum mechanics becomes important, and f is the frequency of the light. So light frequency f we can think of as a wave. We can also think of it as a particle made up of, well, as a stream of particles, where each particle has an energy E, which is equal to hf. And since we're looking at the wavelength for physical matter, we can ask, what energy does matter possess? I mean, I'm not talking about kinetic energy, so energy to do with it moving. I mean, what inherent energy does physical matter have? And the only really inherent energy it has is energy due to its mass, because as Einstein showed through relativity, mass and energy are, to an extent, at least equivalent. And the amount of energy that a mass m has is equal to E, which is equal to the mass of the object times the speed of light squared. And the speed of light comes up here because the equation comes from relativity, and relativity is all about the effect effects that come from light having a very specific speed, which is independent of how fast you're moving. So we've got our two equations. We've got E equals hf, the energy of a particle of light, and we've got E equals mc squared, the energy of a particle of mass m. So m, again, is the kind of mass of our particle, but we can also think of m as the effective mass of light. Because energy and mass are equivalent, we can say if light is energy, in some very abstract sense it has mass. Now it's not the typical kind of mass, because light moves at the speed of light, which nothing with physical mass can do, but nonetheless light does have some kind of mass because it has energy. And if we divide energy by c squared, we get mass. So now we're going to use these two equations. And we're going to say, well, the energy of a particle is equal to the energy of the particle. And because of that, we're saying h times the frequency of the wave of this particle must equal the inherent energy of this particle, so it's rest mass energy, so mc squared. Now, we know from looking at waves that the frequency of the wave is the speed of light divided by the wavelength of the wave, so we can substitute f equals c over lambda into the equation second from the bottom, and we get the bottom equation. And that just comes from thinking of speed equals distance over time and thinking of what is the definition of the wavelength, how far is that, what's frequency, what kind of time does frequency refer to, and essentially using speed equals distance over time, you get f equals c over lambda, where c is the speed of the wave and lambda is the wavelength. Now we can divide both sides of the expression by c, and we're left with m times c equals h over lambda. Now, because we're talking about like the wavelength of, well, really anything, it could be light, but it could also be an object with rest mass, and therefore I'm going to now replace c, the speed of light, with v, which is going to be the speed of a particle. If it's a particle of light, that would equal c, but it might not be. It might be a particle moving very slowly. And when I do that, I get the mass times the velocity is h over lambda. So lambda, my de Broglie wavelength, the wavelength of physical matter, is h over m times v. And m times v is sometimes called the momentum, so we get wavelength equals h, a constant in quantum mechanics, divided by p, the momentum of our particle. So something with a very small momentum has a larger wavelength than something with a very big momentum. Although because h is so tiny, for lambda to be big, and by big I mean like big enough that the wavelength, is a distance which we can see, the momentum would have to be ridiculously small. I mean, even for an electron, which is a really light particle and therefore has a very small momentum, its wavelength is still on the scale of atoms. It's not a macroscopic scale. And so we don't see macroscopic things displaying any wave-like behaviour really, but we see electrons displaying wave-like behaviour as they're passing atoms. They can diffract through things or the spacing between atoms because their wavelength is of that kind of size. And the natural question to ask is, well, what's waving? We have a wavelength for matter, but what does it mean to talk about the wavelength of a particle? What's waving? And the thing that's waving is the wave function, and if you would like to hear more about the wave function, please look at my other videos. Thank you very much for listening to this video. I hope this has shown you a kind of neat way to get to the equation for the de Broglie wavelength. But very much a big thank you for listening, and if you would like to know more about wave functions or quantum mechanics, please check out the other videos on my channel.